I'm talking about atomic dark matter. Let's get into it. So what is atomic dark matter? Here we're working with a sort of minimal model. So all we need to assume is that there's two new fields. We've got a dark proton, dark electron. They're coupled under some new U1 gauge group that gives us a coupling alpha dark. Very analogous to the standard model. This is just sort of E and M. And so of course we can form bound states such as dark hydrogen. And so these are the sort of three microphysics parameters that we're working with in this model. We also have to consider some cosmological parameters. So we assume our ADM is some fraction of the total dark matter budget. So everything else behaves like CDM. And then our fraction defined by this FD parameter is atomic dark matter. And lastly, we need to assume some primordial temperature asymmetry between the dark photon and standard model baths. This is essentially because the temperature asymmetry is equivalent to a delta ineffective bound. So if it was exactly the same temperature, we'd already be entirely excluded by CMB. So we just have to assume there's some asymmetric reheating going on in the background. So just to summarize, our model has 5 parameters, 3 microphysics parameters, 2 cosmological parameters. And additionally, we're assuming there's some asymmetric Kralik abundance. Again, this is just like the standard model. There's some baryogenesis mechanism going on, but we ignore that or like don't get into it. And then lastly, in this minimal model, we assume there's no dark nuclear physics going on. So this means we have our dark hydrogen, but we don't worry about further states forming dark nuclei, dark feedback, all those sort of problems that could start to arise. So we keep it simple. And so importantly is like, why should you care about this model? And I think a good sort of motivation sort of perspective to have is, I'm going to say dark matter is a particle. Well, we know 10% could be PBHs, rah, rah, rah. Hope that's not too controversial. But we should be looking to issues in particle physics to motivate what we're considering for dark matter candidates. And so of course, so for the last sort of few decades or so, the hierarchy problem has been one of, if not the biggest unsolved problems in particle physics. And essentially boils down to why is the Higgs boson so light? And as I said, this has been a guiding principle. And so if we sort of look back before I was born, SUSY was popular, and SUSY ties into sort of why WIMPs did kind of get the popularity that they did as a cold dark matter candidate, because particle physicists could point to a model that motivated the WIMP as a good dark matter candidate, which motivated CDM, and you can say the same thing about the axion. SUSY hasn't remained popular in the last few years, of course, since LHC sort of hasn't found anything. And so this motivated a new wave of sort of models to address the hierarchy problem. And so one such family sort of neutral naturalness, and I'm going to point to the twin Higgs interpretation of a neutral naturalist model as sort of benchmark. And how this works by solving the hierarchy problem is essentially adding an additional copy of the standard model into some new dark sector. And so very simply, we can see we'll have some sort of bath of dark protons, dark electrons, dark photons, and then you can see this is how we get sort of atomic dark matter operating in a dark sector. So I just want to keep that sort of narrative logic of, if we start from the hierarchy problem, we look for a solution, either it be SUSY, neutral naturalness, this is how we get our motivation for atomic dark matter. And what I'll show you throughout this talk is sort of, if we have these simple extensions to a dark sector beyond just sort of simple CDM, WIMP-like, we can have drastic astrophysical effects, which of course is how we can constrain new physics, but ultimately could be our avenue for discovery. And so just to sort of show 2 paths with how we could think about atomic dark matter, as I said, we start with a sort of simple dark sector. We have 2 fields with a mass splitting and it's charged under some unbroken U1. You can think of these as sort of fundamental particles. This is a very generic minimal model. Lots of literature that I've sort of partially cited, many more. But even from this minimal model, we get sort of a lot of interesting effects. So I've sort of broadly broken down into 2 main groups. So we can have sort of on cosmological scales, we'll have dark radiation contributing to ineffective, but sort of more importantly, we get these dark acoustic oscillations or DAOs that will show up in the matter power spectrum, as well as a suppression of structure formation on small scales. On the other hand, we have astrophysical effects. And so this is similar to the way standard model baryons can cool and dissipate energy. Now we can have a dark matter component observing the same dissipation, which will affect galactic morphology or subgalactic morphology. On the other hand, we can sort of consider this path we think of more along the lines of the twin Higgs model. And so I'm saying this is sort of baryon-like physics where our dark proton is no longer a fundamental field, could be made of dark quarks, and then you start opening up sort of Pandora's box of dark neutrons, dark nuclear physics, etc. But the main point I want to say is, even if we have this sort of model, it still gives us the same cosmological and astrophysical effects we can still look for. It then just opens up, as I said, mirror stars, dark nova. Daunting, but exciting, but sort of beyond the scope of the talk for now. I'm just going to mainly work on the minimal model. But the point being is that ADM works as both a general study of sort of features of dark matter with dissipative dynamics, but you could also think of it as a specific realization of a motivated model. And so now I've talked about the parameter space, but now we've also got lots of scales, lots of redshifts to actually look for this in observables. And so I just want to point out, so we've started to do, or there are existing studies looking to say CMB bounds or galactic morphology of ADM, and that as you move into sort of more recent redshifts, you're entering the nonlinear regime. And so of course, this requires n-body simulations and motivates incorporating these alternative dark matter models into hydrodynamical and n-body simulations. But I really also want to just pause on this, because if we're looking for atomic dark matter, where do we start? And so as I said, we could have broken down ADM into sort of having two major different effects. So first we can look at cosmological effects, where of course it's going to be important at cosmological times. As we move later at high scales, tends to get washed out, but could still exist, have a suppression on smaller scales. And then on the side of the ADM parameter space, while there could be regions of parameter space where we do have strong cosmological features, so that's where we can have DAOs. But on the other hand, if ADM recombines really early, it's just going to behave like CDM. So then we can simplify the problem and just think of a CDM-like transfer function. Additionally, as I said, we can have astrophysical effects. So at late times and more galactic scales, this is when we may have to worry about ADM cooling. Or if ADM cooling isn't efficient, we can still just use standard hydrodynamic simulations. So I want to just sort of motivate this idea of breaking down our ADM parameter space, since it's so hyperdimensional in 5D, to sort of these sort of simplified regions where we can assume, is ADM cooling relevant or not? Is cosmology relevant or not? And that's how we can target different experiments to look for these observables. So now I'll just sort of go on to more of the specifics of the cosmology of atomic dark matter. So first of all, I've sort of mentioned dark acoustic oscillations, but what are they? So since atomic dark matter is this dark plasma coupled to the dark photons, as an overdensity wants to undergo gravitational collapse, dark photon pressure opposes that and can support it. So this creates this oscillatory phase. And so you can see here, if we have blue CDM, it naturally just grows, the overdensity grows in time, but ADM will get stuck, go through this oscillation, and even as it exits, because ADM has recombined, will lead to an overall suppression in the growth of that overdensity. And so this is characterized by the DAO scale or the dark sound horizon. And so we can look for this because this sort of imprints itself on the matter power spectrum. And one thing I really want to hammer home is that this is a unique signature of dark matter or dark radiation coupling that is present in ADM. Because I mentioned that suppression is present in the ADM transfer function due to the DAO scale, but this is sort of degenerate with other dark matter models, while the DAO oscillations is actually very specific. It gives us a nice sort of pinpoint signature to look for ADM. So if it's showing up in the matter power spectrum, we can of course look to CMB measurements to constrain this. And so this is one of the first studies for ADM, fractional ADM. And this was possible due to Jared Barron implementing an ADM in class. So I really want to emphasize that to do these studies, you really need to take the existing CDM technology and put in the effort to adapt it to handle these alternative dark matter models. As you can see, there's a strong bound on the delta ineffective or temperature from cosmology, but in general, it's still, most of the microparameters are weakly constrained so far. But we do get a strong bound on RDAO, and that's the scale at which the oscillations are entering the sort of sound horizon. But if we want to go further and constrain RDO to smaller and smaller scales, that's when we want to look to later measurements, such as the UV luminosity function. And so this is just capturing the abundance of galaxies as a function of their luminosity. But this is important in sort of depicting how we can break down our approach to ADM into both sort of cosmological and astrophysical effects. Because here we've got the halo mass function, which is just essentially the number of dark matter halos and their masses. And this is entirely determined by the matter power spectrum because the ADM will suppress structure at smaller scales. On the other hand, we've got the halo galaxy connection, which is essentially the relationship between the dark matter halos and the mass of the galaxies that they host. This can be done, calculated using the Zeus 21 code by Julian Munoz, but it depends on astrophysics and stellar formation assumptions. And this is important because if ADM is cooling, this could change how early the size of and densities of early dark matter halos, which would change the galactic formation, could change star formation. And so we will have to assume that there's no ADM cooling on to sort of use the standard model assumptions. But it does break down into very simply, we've got astrophysics effects on one side and the cosmology effects on the other side. But we can use this UV luminosity function to compare to JWST data. And this is just some preliminary work for Jared. Full scans coming soon, look out for that. But you can see ADM is suppressing and causing fewer faint galaxies due to that structural formation. Additionally, for sort of late time cosmological observations, we can look to the Lyman alpha forest. We've already heard a lot about that. But it's essentially measuring the clustering of neutral hydrogen in the IgM. And again, this is a tracer of the underlying dark matter halos and probes the DAO scale. And so again, there's this sort of idea of separation between cosmological effects, where the DAOs will be imprinted on the matter power spectrum and inferred from Lyman alpha, but then we still want to focus on this non-ADM cooling regime because, again, if ADM is cooling and changing this formation of halos in sort of the 10 to 20 redshift range, this is going to affect star formation, affect reionization history, and also come into the measurement of our Lyman alpha forest. So you want to sort of separate out the regions of parameter space that have strong cooling effects. And so one thing I just want to sort of emphasize with Lyman alpha is that it appears to be uniquely sensitive to probing these DAOs, which makes it really good for ADM. And so this is from an early ethos paper, where you can see here at Z equals 6, we have this peak, which is the sort of oscillation scale. And as we even go to Z equals 3.6, we still see this increase present. And so me, Linda, Kier, other collaborators in the audience, we're also working on a Lyman alpha scan using this ADM gizmo. And so we want to sort of test this out and sort of preliminary work. We just start with a power spectrum at Z equals 99, our initial conditions. And so we look at two different approximations of our power spectra. We have blue, the full oscillations. We do sort of a one level approximation where we just capture the first peak. And then we do a just complete approximation. We just do the suppression scale, averaging out the oscillations. And so if we look at the 3D matter power spectrum again, after evolving using Gizmo at 4.6, all the oscillation features have washed out. And the difference in our approximation just depends on how suppressive, but as you can see, very small differences. If we actually calculate the 1D flux power spectra using fake spectra, which sort of mimics the Lyman alpha signature, we actually see quite a big difference between this full approximation and capturing this first peak. And there's actually not much difference between further peaks at much larger scales. So this is why Lyman alpha, as we heard already, could be really good at testing dark matter in general, but could be also even better at testing atomic dark matter. So having done a survey of sort of cosmological studies, I'll now move more into the sort of astrophysics of atomic dark matter. So the most important feature of atomic dark matter for astrophysical sort of scales is the dissipative physics. So we know that after recombination, ADM will form neutral dark hydrogen, fall into dark matter halos, shock heat, reionize. I mean, this is all the same standard picture that we know from the standard model. But essentially they can cool, given by these cooling functions here through various processes. And this will allow them to radiate away energy and sort of collapse into the center of the galaxy. And so we can also include molecular cooling thanks to sort of the Penn State group. And this gives us a full way to calculate the cooling dynamics of atomic dark matter. And as I said, this is important because this will affect ADM galactic morphology, because we have our sort of spherical halo with the gas in it. It'll radiate away energy through its cooling physics, but of course it has some net angular momentum. So we could think that this could lead to a dark disk formation, or other people have considered that it could form dark gas fragments. And that's just because due to the cooling could be more aggressive in various areas of the parameter space, or just through merger events. But essentially this was an open question for a while of like, what will actually happen for atomic dark matter on galactic scales? And so the collaboration wanted to address that, and this sort of led to the work of primarily Sandeep Roy implementing ADM in Gizmo. And how that was done was essentially, we usually think of CDM in these simulations as just being point-like gravitationally interacting particles, but now we essentially can copy over the standard model gas and have this subcomponent of ADM as well with these gas cells that have pressure, volume, temperature, that's what I was meant to say. But then these can cool through the cooling rates determined by the previous slide, and then ultimately form clumps because they've gravitationally collapsed. And these are sort of, could be mirror stars, could be dark compact objects, but they're beyond the scale of our resolution. They're just back to being only interacting gravitationally. But what I mean, in this first work that Sandeep and collaborators sort of carried out, is they looked at the galactic morphology of two different sort of ADM parameter points. And so you can see that it can form dark disks, the ADM gas component, but they're also not thin, which was sort of an approximation that was used earlier in the time to test this sort of dark disk theory. But also more importantly, is that it can easily destroy the Milky Way, as we've sort of heard throughout the day. And that you get this little tiny little baryonic gas disk for the Milky Way. But also what's important is that between ADM1 and ADM2, those parameter points, it's a factor of 2 increase in the coupling strength. So one factor of 2 increase in the coupling strength can have drastic implications for the galactic structure, which of course is sort of intimidating if you want to explore this 5D parameter space and realize how sensitive you are to small changes, but also motivates just a better understanding, of course, of mapping up this parameter space and working out where are the aggressive cooling regimes, where are not the aggressive cooling regimes. And you'll see that this has led to some future work. But also just want to point out that while the gas disk did form, most of the ADM actually cooled into those clumps that we talked about and sunk to the middle, the sort of central potential of the galaxy, and really messed with the circular velocity profile. And this could be another sort of probe for atomic dark matter physics. From these same simulations, we also looked at the subhalo distributions. And so you can see ADM can have a large effect on the number and radial distribution of these dark matter subhalos, where we have sort of a large increase in these inner sort of 100 kiloparsecs. And so to further sort of look into that, we looked at the orbits of these subhalos. And so what we called the enhanced compactness subhalos, which is sort of ADM rich because they have around largely 30% fractions of ADM, they tend to have much smaller pericenters and smaller apicenters. So they're just really circling close to the center of the Milky Way galaxy. And I just want to point this out because, of course, motivates further study because we'd love to look into this more into sort of deeper dive, but it could be really interesting for stellar stream searches. And so the big sort of takeaway I want people to have from this work, this talk, is that, so Sandeep went on to do this dwarf galaxy paper where he looked at the aggressive cooling regime. And so importantly is they introduced this effective parameter that quantifies ADM if ADM can cool on galactic timescales. And so this is sort of going on beyond individual simulations and creating an analytic expression that allows us to mark out the aggressive cooling regime in 5D parameter space. And so what they found is in this regime is they look at a variety of simulations in this aggressive cooling regime, and you can see that they all sort of pretty much asymptote to this inner slope. So in this regime, there's sort of this equilibrium state where all the dwarf galaxies have the same sort of density profile in these inner regions. And so yeah, as I said, it's going beyond the individual simulations and making sort of the entire parameter space tractable and breaking down the 5D parameter space into regions where we can work out what is aggressively cooling and see there's these sort of equilibrium conditions reached that we can generalize to sort of large swaths of our parameter space. How am I doing on time?
Yeah, you're good.
Okay. Okay, sweet. So yeah, just sort of like the last little bit is looking at smaller sub-resolution scales. So yeah, these are below the resolution of these simulations, but you can also think of the formation of mirror stars or dark compact objects due to these dissipative dynamics in the dark sector. And so just sort of like quickly flash up sort of different searches you could do. So of course you can do microlensing searches, where essentially these dark compact objects will just pass through bright spots and create micro gravitational lensing. And so this work showed that LST should be able to constrain 2 sub% level fraction of dark matter in these compact objects, whether it's in a spherical or dark disk configuration. If you want to get a bit more exotic and start to reach into this dark nuclear physics territory, you can start to think of mirror neutron stars. And then of course their merger events will create gravitational waves. that you can sort of try diagnose and look for. But also what's really fun is that if you assume some small sort of mixing or interaction with the standard model, is that if you form mirror stars, they'll be essentially able to sort of like vacuum up the like intergalactic medium as they sort of pass through and capture it in the middle and sort of shine back in standard model photons. So you can literally draw an HR diagram. Here's the classic sort of main sequence, and that mirror stars will be shining in this completely sort of independent region, which is possible to look for. So to conclude, I just want to emphasize that atomic dark matter provides a specific example of a theoretically motivated dark sector, but also is sort of more generic and allows us to study the effects of dissipative dynamics. And sort of the two main sort of features, as I said, is like on the cosmology side, we've got DAOs, which is uniquely due to the dark matter radiation coupling. And then on the astrophysical side, we've got these dissipative cooling dynamics that is really important for the galactic morphology and subgalactic scales. And so motivating further studies into these hydrodynamical simulations of ADM. But importantly is like testing ADM with these astrophysical studies is a viable way of probing what could be the new BSM physics. And so just sort of what's next is we're attacking ADM from all these angles. As you see, there's a lot of ongoing studies trying to carve away from different regions. But this will allow us to then better understand the behavior of the remaining available parameter space, which will allow us to motivate targeted searches, which could be as points of discovery. And so dissipation has started to be implemented in in-body simulations or hydrodynamical simulations, but we can look, there's much more work to be done. We can to develop past this minimal model and some of the approximations that have been used in the cooling physics. But I wonder, like, we have come a long way and remind people, it's like, there's now possible a complete pipeline to go from class simulations in ADM to generate initial conditions, using these initial conditions into Gizmo simulations to do these sort of front to end sort of pipelines. But yeah, lots more to do. Thank you.